So we'll talk about stack and queue. You probably, I don't know if Harvard, I think, covered stack and queue in a moment, in a little bit, right? So what's a stack?
I mean, like a stack.
It's stack, right? Yeah, exactly. Like books or plates, of course. They're always plates. Yeah. Last out for last in, first out.
Yeah.
LIFO, right? Last in, first out, right? The only thing is how do you implement it, right? So how would you implement a stack, right? Well, what could you use? What could we use, right? We don't have a stack right now. We want a stack.
We'll just take an array.
Yeah.
And give it a couple of methods, such as
Yeah.
insert element and insert would mean to add it as the last element.
Yeah. Okay.
And
But
then remove element would be just remove the last.
okay, that sounds easy. But the only problem is if you're doing C++, how about memory? If you have arrays, they're fixed size. So if you run out of space, what do we do?
Allocate more memory.
Yeah. All right. Good. So how do we allocate more memory? How much memory should we allocate more? How much more?
At the size of one element.
Okay. And then we want more and more. We allocate again.
Yes.
Okay. We keep doing it like each time. Yeah, we could. I mean, we could allocate more memory like this. But it turns out in the practice, that's not very. It's painful to allocate memory each time. You know, you have 1 million element, stack, and you need 1,000,001, right? Reallocate. It's kind of expensive operation. So instead, what's usually done, you multiply by some value, usually in powers of 2. So if you have 1,000 elements and you need 1,000 in the first element, you allocate 2,000 elements. Then you have some room. You kind of assume you have plenty of room, so you keep doubling up basically, right? Sort of like allocate with some extra basic space. So that's one approach. So, well, another approach, what else could we use for our stack structure? Last lecture? We could use vector, of course. You could use a vector, of course, because the vector is already really nice. Vector does all the thing for us already. But something that you did in last, what did you do? What did you talk about last lecture? What structure?
Linked list.
Yes.
Yeah,
We could do that, right? It's all. If you have a linked list, we don't need to. It's pretty much a built-in stack, basically, right? The only question is what kind of list can we use? Can we use single linked list, right? With single directions? Could we?
Yes.
Yes. Okay. But now the question is.
You have to insert at the beginning.
Yes, exactly. That's one of the things. With a stack, if you want to have a stack with a linked list structure, maybe I'll do my favorite paint, right? I do my paint app. I know you love my painting skills. So, right. So let's see where do I have document here from previous lectures. Complexities and PDFs, more money. Where are my buildings? I know I saved it somewhere. Pictures, vectors. I thought I had it. Maybe I don't anymore. Oh, there's graph. Oh, double linked list. Okay. Oh, that's not registry. It's reg or something. Okay. I guess I'll have to I have to draw again quickly. I'll do like quick painting. Right. So we have a linked list, right? Fat linked list. Right. And we have tail. Right. Next, right? And we have some, tail. Well, actually, this would be Control Z. We have a tail pointer, which is not really useful, right? Tail. And we have a head, right? Head. Okay, right. So of course we have a null pointer here, right? Null pointer, right? I'll do T, null pointer, right? And we have some data here. We have like maybe, I don't know, 5, something, on some data, right? Okay. Head, so this could be used. We could consider it as a stack. So the problem is like including things that even if you have a what's the issue is putting things in a tail, right? We could, if you have a tail pointer, we could, right? But the problem is removal, right? How would we remove things from the tail on a singly linked list, right? Not so easy. So the solution is simple. You put stuff in the beginning, and it has nice some advantage. It's all one. You know, the linked list takes care of allocation. Of course, yeah, it's always one by one by one by one, right? So basically, let's say I have a new item. I'll draw it again. I'll have a new item, right? In comes some number. I don't know, 9001, right? Oh, not. I want to put. So basically, what do? I move the head here, right? Right. And here, I'll take my trusty. Well, I should probably do this first. When I'm coding, this will be done first, right? And of course, I also need to add it here, right? The order matters, right? The actual implementation will matter, but of course, we don't have to worry about it because we already have the linked list structure doing this for us. We already have all the methods defined, right? And we have a right. It's a last in, first out, right? So this, if you want to remove it, we simply move the head pointer here and delete freed up memory for this, and that's handled by the regular linked list instruction. So again, stack can be implemented in an array, and it can also implement in a linked list. Now, which one should you use? If you actually had to make a stack from scratch, I don't know if you're working some really low-level system which doesn't have anything, you just have a, I don't know, probably even C, probably doesn't have even C++, probably has just C. That's what you do. You have to do something like this. But of course, in real life, you can just use a vector. It's nice. You have also a linked list. I think you only have a link. You have a stack structure. Let's take a look here. Plus reference. There's stack built-in stack container. I think it's already here. Yeah, it exists. It exists. So this is what you would use, right? In real life, use this, right? Meaning, if I'm not asking specifically, if it's not prohibited, you can use this, right? How it's done, all right? It includes what? Empty and capacity. So this smells to me that underneath there is probably a vector or maybe even a C-type array, right? Empty capacity, right? How much, right? How many members, right? If it's empty, how many, right? It smells like this, but it's of course nothing. I don't think it's said how it's done, right? Yeah. So push back, but yeah. Vector, right? So it's using a vector probably, right? Maybe actually there's a deque actually. There's actually something more generic. That's a deque actually. So stack is sort of like actually I think inheriting from the queue, I think, right? Yeah. So, yeah. So it's you basically you want last in first out. You don't want anything else. But it turns out, I think if you have two stacks, if you have two stack structures, you can do pretty much anything, right? With one stack, you can do everything. You know, in a programming language, we have two stacks. You can juggle them basically, and you can use for pretty much any type of storing any type of data, right? Not fun maybe for some people. It may be fun. There's a special programming language called Force, which is using stacks only. Force programming language, yeah, right? All right, stack oriented. 54 years old the language, right? Some people still use it. Basically, you push things on stack. What's the advantage of stacks, of course, is that you can present arithmetic. You can use, I think, reverse Polish notation, right? Reverse Polish notation. Who has used reverse Polish notation? Does anyone have HP calculator? No? You have probably you have never seen reverse Polish notation, right? When we look next semester, when we look at some of the more esoteric languages, right? Well, or maybe not so esoteric, like things like Lisp, right? Then we'll see this reverse Polish notation in action, right? Again, used to be very common, right? But what's the advantage of this? Because you can present your operations basically. You don't need parentheses. You get rid of parentheses. You present your operations in a stack-oriented format, basically, right? It's kind of like Yoda speak almost, right? Yoda speaks in reverse, right? In Star Wars, right? So kind of like that. Like reverse order. But okay, but you don't have to worry about it, right? Not right now, right? We just worry about stack, right? And you can see how we can then do this in a regular linked list of interpretation, right? So again, we don't need this. There's so many slides. So in abstract ways, right, if we could create an abstract class stack, and then we could have two implementations of it, right? So basically initialize stack is empty, is full, push, top, and pop, right? So top is, I think, gets you the type, right? Pop actually, classical pop operation does not return. You know, like in Python, pop usually returns something, but classical pop does not return, right? So array, right? We can delocate, right? But again, this is abstract data structure, meaning we say what this is, right? And we'll see how we can implement this, right? Let's do this stack ADT. Right, so let's see if we can do this in about half an hour. I think we can. If AI helps us, I think we can. If AI doesn't help us, it will be hard, but we can maybe, right? But we had a list, right? But it's actually not a generic complete. It's not abstract here, right? What we did last time, right? So let's do abstract stack ADT, right? Let's create a definition for abstract stack ADT class, right? We want the following, right? Functions in the derived classes, right? So push pop top is empty. What else do we want? Push pop top is full, is empty. Is empty. Okay, come on, we had it. Is full. Okay, and that's it. So abstract, right? Virtual void, right? So this means, right, I need to, I think we can actually, can I do, I keep messing up with languages. I know in Scala you do abstract. I think in C++ you don't type abstract. I would like to do, in Java you do, and I guess you don't, right? I think this is by virtue of this, by the virtual, right? We get these definitions, right? So this means, right, whichever implements this, yeah, we have to implement these, right? Right, we have no choice around it, right? So class stack, right? We just said, okay, virtual void. Well, okay, I don't like this integer, right? No, integer is not good, right? We also, so all good's over. We want this class to be generic as well. With template, of course, we use template. So template class T, right? On. Now we have some extra abstractions, extra pain, right? So this is a stack, right? Only problem is you just have to implement it, right? So choose whatever poison you want, right? You can use an array, right? Of course, the cheating would be, well, kind of cheating would be to use a vector, right? Of course, vector is great. Again, in real life, use vectors whenever, as much as possible. It's a good structure. Underneath, you have a C-type array, but you have this dynamic allocation, right? And it has been optimized, you know, for most normal uses. Only if the vector is somehow not working for your needs, you would need something your own custom made. But okay, right? Let's do this. So let's create a concrete using array, or let's use vector. Let's use using vector, right? This is the easiest. I can start with the easiest implementation, right? We'll need, of course, import, right? Template class, class vector stack, right? We are on private vector v. We'll need, of course, import, right? Import vector, right? Import vector. IO stream and import vector. Yeah, include it, not import. Sorry, include. Yeah, of course. No? Now this should be legal. So these are privates. So this means that publicly, so this is the idea of data hiding, right? Public, this means us who are going to be using this, you know, their friend who's going to be using your stack class, right? They don't have to worry about how do you do this underneath, what kind of dirty stuff you do underneath. In private, right? we only care about the public face, you know. In public you are very nice, well-mannered person, right? In private you're doing I don't know what, right? So that's we're looking at the private. So vector, so that's the implementation detail. So these are, so private is the implementation detail, which public, yeah, while public is the public is interface, right? So this is a big approach. Again, why? Because you don't want to expose unneeded complexity to the outside user. And again, outside user here being another developer, including yourself, right? You don't want to, again, with good reason, you don't want to peek inside. With Python, it's really hard to type. With Python, it's really hard to hide this, right? Because Python is so loose. C++ gives us more fine control, right? So this is here, right? So let's take a look. Now to private, capacity, integers or size t. Again, I would use size t actually, of course. Again, I like size t, right? Integers would be size t, right? Public. So now the actual work starts for us, right? Now we actually have to do something, actually, right? All right. So push value, right? We have a vector. This makes things easy for us, right? So push value. Let's now we implement the interface, right? Vector stack, size capacity. Let's see. So this is what? This is a constructor, right? We have push, right? Capacity, and we can. The thing is now vector stack. This means we have to add the capacity is given, right? This is a maximum size, right? We don't want to I mean, again, is this necessary? Maybe not. I don't know. We could think about. Do you want to have default? Maybe. Let's think. So push is really easy because it's only given, right? If size is less than capacity, but we do have some sanity checking, right? This capacity serves as a maximum, right? We push back, right? Pop, easy, right? Remember, pop in a vector does not give you the value. So this, this works, right? Pop back, right? Size over 0, we pop back. Size minus, right? Top, if size is more than 0, meaning you have something, so you return the last item. But again, you return it. You don't delete it, right? That's why in classical stacks you have these two operations, pop and top, right? Python combines them, right? In Python list, for example, right? Here you have both, right? So notice, so pop, yes, question?
So is that a good approach to, in the top method, can you scroll a bit down?
Yeah.
To return minus.
Okay.
Because what if my
this is
vector array contains minus 1?
Yeah, I don't okay, so let's look at this. So this is a good question actually, right? So because we have t, right? We're actually returning t. This actually also is a problem, right? If this is actually a string, right? We're storing some strings in a stack, right? This is actually going to fail, right? Because we're returning actual, right? Vector is storing t, right?
Yeah.
Data type. So this problem, actually, this looks like a problem. The question is, what can we do actually here, right? If it's basically an exception. This should be an exception, right? We should be really raising an exception, right? What can we return actually, right? We could return whatever default for t is, but we don't really have a way of getting this, right? So this is like an error condition, basically, right? There's not really a good way of out of it actually. We could see what does let's check what the queue. Let's see what they do here. Top here, right? Pop. It doesn't have it, right? Remove the top element. Push range swap. Can we see? Let's see this one here. How does pop work officially? What do they do? Actually, pop back, right? Access. Okay, that's what they are doing. Top. Okay, let's see. Public member. This is what this is what we could remove, right? So what is a signature? T, right? Let's take a look. Top doesn't say anything. What happens if you don't? Reference to the last element, but and also the thing is we actually probably, if you want to make completely generic, right? I mean, if you're returning some very difficult, if you're storing like, I don't know, some objects, some difficult objects, right? You probably want to just reference, right? So it should really be returning reference, right? It should not be copying it, right? Right? Because it's a good question actually. What should top return, right? So this -1 is kind of really sus, I would say, really sus. So this is what can we return on if the stack is empty, right? Well,
Proper programming languages you could null.
yeah. Well, I mean, we have null. We could return null pointer, right?
Yeah, that could work.
Yeah, I'll do null pointer, right? Right. On return, right. And this is of course this is also a pointer, basically. You know. So this should work for now, right? Right. For now. Right. So, okay. Is empty? Is easy? Is full? Is size? So this is again not completely easy solve. So it's easy. Is full size capacity. So this means basically we have a vector handles this, but we don't have. We have a fixed size stack. So this is fixed vector stack basically, right? We have a constructor, right? And now we can try it, right? Let's try this. Now let's see our stack in action. And again, but we will use again, right? Vector stack integer, right? We say, okay, we're going to be storing integers, and of course, pop, push, and how much capacity? 5. What's going to happen if we push? Right, push back. So this means here it's void, right? Since it is void, the stack, full stack will not do anything, right? So in a way it's safe, right? We keep pushing until we have nothing, right? And so again, do you want some errors? Basically, right? You probably could be some error messages, or maybe something could raise an exception if stack is full, right? That's possibility here, right? If you want to make maybe nicer, user friendlier for those who like exceptions, right? I know you guys doing your homework with exceptions, right? So, yeah, okay. So again, so seemingly simple structure, but lots of things, things to consider if you want to implement yourself. So vector T, what's the problem here? What doesn't like it? Line 68. Vector stack. Let's try compile it. Well, this is AI has gotten a little crazy. We don't need this. We need this. Right. Let's not push too much. I mean, it's just silly, right? This is all, nothing's going to happen here, right? What do they expect, right? Why? And print. Now, let's print until empty. While stack is not empty, count, right? Stack pop, standard. Okay, using stdio. Yeah, using st. All right. Now, what's template? Okay. Everything looks okay. Let's compile this. This I don't know, monster or beauty. I don't know. So let's see if it actually compiles. G++, and we're gonna add all error checking and abstract all warnings should be cleared as errors after stack and auto ADT stack. I'll call this ADT stack. It will compile on first try. No, it does not like it. Okay. Let's take a look at this point here. All right. So now T. Right. So how would we can we cast it to this? So this is the tricky part. This is your question answer. So in line 58, right? We are returning where is this? In implementation, right? This part here. So, but we need to. I think we need to cast this type. We will need to cast. We will need to cast it to the type of the stack, right? Can we do this? Reference. How will this work? Is this? I forget now. Is it like this? Oh, is this legal? But then we need a difference to this. No. Cast from. Oh, okay. Lose precision. It's a warn. No, okay. Is it warning or error? It's an error. From null pointer to integer lose precision. Okay. An error. So what else could we cast? Or can we cast any? Okay, if I put -1, right? The problem is we can't. The thing is, we can't really return. We return, right? We would like not to do anything, right? But we are forced to return something. So what can we return in general case? There's not really. Trying to see what would be a good solution to this, right? If we don't want to do exceptions, right? Because it's not something we want to do, right? We just want to basically return immediately, right? If size we return, right? Right, F permissive, right? So this becomes strong, right? So I'm casting null pointer, right? So let's see if this error, right? What does Stack Overflow say about this, right? I can't copy. I copy this, right? Come on, Control C does not work in code spaces. I think it works. Okay, let's take a check. Take a look. No, don't save it. Yeah, all right. Let's see what Stack Overflow. You know, these days I use Stack Overflow very rarely, actually, but it still has, of course, right. From void to int, right. Right. So let's see. So we are recasting. So this thing is. Right. Cast this first. Okay. Yeah, this is a crazy answer, but this is C language, C++. This is a casting. You know, this is like 15 years ago. Older compiler version, right? We are in like 6 something now, right? Let's see, what version are we? We are on 6, 9, actually version 9 for Ubuntu. That's how it, yeah, 9.40 apparently, right? Okay, for Ubuntu 20. Okay, so there's, you know, it's been a lot of changes, right? But would like to cast, right? So this thing here, yeah, but basically, yeah, we want to return the address. So let's see, we want to return the address, right? But we want to have constant, right? Address, right? Top. Let's rewrite our top, right? Well, actually, let's redefine it here, right? That top should return a reference to top element. So let's rewrite this. I think is it correct? I'm not sure if it's correct. Virtual, yeah, T address. I think that's more appropriate, right? Reference, and now, of course, pop, right? Push. Now, yeah, return v size. That's one way of doing it. This will compile, right? How about if stack's empty? All right, or let's return a dummy value. null pointer. Cast to T. Okay, let's do this. If size, okay, so this is a trick. Look at this. Look at this crazy magic. This might work actually, right? Again, null pointer, but you have to cast this type, right? So this means, of course, so this is basically what this means is if you are doing a top and you get this, right? Well, it's up to you to check this address, right? So you're passing the responsibility, right? There's no real good way of handling this case, right? So, because how do you, this is an issue. How do you pass this information along if you are promising to send this, right? So, let's take a look now if this compiles finally. I don't know. It compiles, yay. All right, so now we can do our stack. So, what was it, ADT stack? Yeah, 8.7. So we push a bunch of stuff on. We popped everything, right? So yeah, we pushed everything and we popped everything out, right? Again, the key point of stack is you cannot peek like 6 values deep, right? You have stack, you only get access to the top plate, right? Only the top plate. Now, where is our slides, right? So hopefully you saw how easy this to do. Now we also have another structure, which is of course Q, right? So what's the difference between Q? Q. What's different from Q from a stack? First out, yes. It would be kind of really evil if you went to like a movie theater and it was a stack-based operation. Whoever comes in last gets the ticket first, right? Not so cool, right? You want a queue type of structure there, right? If you're going to in a supermarket and you sit standing in a line, right? So yeah, in real life, where would you use stacks like in real life situations? I don't know. Where would be? I don't know. Where would be? Like last in, first out. Where would be appropriate? Like I'm talking about, human interactions, or I don't know. Like, well, I guess stacking plates, right? I suppose, right? But it's also, it means that the first plate, whichever you put last, right, always gets used more than the one at the bottom, right? You have like 10 plates at home or on your shelf, right? You always take the top one, right? And the bottom one never gets used. And then one day you decide to take the bottom one and you break all 10 plates, right? They all fall off, right? So, but yeah, so if you think of a good application of stack in a real life situation, maybe, I don't know. Any ideas? I don't know, maybe some. But yeah, so, but of course, as far as systems, as far as programming, you use stacks all the time, right? So again, same idea, right? But first in, first out, right? So how would you do this in a vector? What do you think? Like in a linear? Okay, first of all, how about a queue in a linked list? Well, kind of pain, right? Well, but we can use it, right? But deletion is a pain, right? But actually, it turns out we can use it, right? So because what we do is, right? So where is it easy to delete? Deletion is easy where? Head, yeah, head is easy to delete because you delete this. And you save, where the head, right? You know where this is right now. You save temporary, you move the head, and you delete then the temporary reference to this data, right? You don't have anything dangling. And then, well, removal. But addition, you added a tail. So yeah, you can use a singly linked list as a queue by adding a tail, because additional tail works, right? You add a new item, right? And you move it, right? So that's possibility, right? But of course, doubly linked lists will be easier, right? Doubly linked is very easy. You're not going to worry too much about losing some references. You still have to worry, but not as much, right? And of course, also we can use a vector, but vector is a little bit trickier, right? How would you use a vector? Let's say you have a vector of size, I don't know, 1,000 items, and you want to have queue, right? Is this possible and you have a queue of people keep coming in, keep coming out. So what's the trick? I can show you in a moment, but think about it. Well, what can help us? If you have a vector, right? Or fix, we know the size, right? So you have 1,000 people came in already, right? And well, like 10 people already been served, right? And 5 people come around. What do? Well, you have fixed sized, right? Let's see. Let's draw a picture. A new picture again. Oh, no, don't save this one. So you have a vector, right? You have I would like to draw some people here, but I guess I won't, right? Right. No, I can't draw. Okay, now I'll just copy and paste. I should copy and paste this, right? Right. Control C, Control V. Oh, there you go, right? And you have here, right? So it's full of people, right? I'll do this. Oh, Control Z, Control Y. Okay, that doesn't work. This doesn't have much. Again, I guess I need I need Photoshop or something which has some layers and things like that, right? So what I'll do is I'll do copy, paste, right? Control C, now I have Control V, right? Now I have 4, right? And now I do 8, right? Right? This is the same approach we are using for allocating memory, right? So now I have, right? Now I have 8 people, right? Standing in queue, right? And now 16, right? All right. Save some time. Okay, but yeah, so the issue is, right, this is a vector, right? This is a vector, I'll to say this is a vector, right? Now, what happens, so, what do we do if somebody, this guy is first in line, right? He's gonna get the money, right? Or, there's money, or whatever we call it, right? Not text, you, come on, home, right? There's a big pot of money, right? I'll do like, no, right, and he's first to get it at the bank, right? Bank, right. So what's the idea? So, can you think of a solution to this?
Can't we just store the index of the person coming out?
Yes.
And then
yes.
so adding one to it.
Yeah, so basic idea is, yeah, we need to basically store 2 references. To the last person and the first person. And you say, okay, but how does that help us? Well, okay, let's say we're going to remove this first person. He's going to be happy, or I'll just cut him off, and he's in the bank, right? Control X, right? He's inside here, right? He's here, right? Okay. Come on, Control C. Okay, I'll do one more time. He's here, right? Okay. Or he's gone, basically. Okay. Right. But basically, right. So what we do is we have pointers, right? We have pointers. Hope you like my pictures, right? So this is the first, right? First, right? And this is the last, right? Right. So we know this guy is the next one to be served and get his money, right? So these are all creditors to failing bank or something. Okay, but yeah, so more people are coming in. So what happens here? So let's do a cut, right? So I'll do like 4 more people. I'll add 4 more. Control C, Control V, right? All right. So it seems like full, but the thing is, there's empty space here, right? So what do we do here? Again, I will cut this off and say last guy is here, right? That's easy to do. The first guy here. Meanwhile, this guy is gone, right? He's gone, he got his money, he's happy, right? And also this guy is gone, right? He's also happy, right? He got his money, right? So of course I move this, right? I'll move this to here, right? Now, but so what do we do if there's one new person comes in, he wants his money, right? Do we just send him away, or what can we do?
You put him on the front and
yes, yeah. So basically, we don't remember moving stuff around is expensive, but since we have this fixed size, we can put this first guy here, right? This new guy, we'll put him in orange, right, or something, right? I'll draw another guy. Maybe this is a girl, right? So right? Very good picture. Right, okay. So you move the pointer here, basically, right? Reference, or called index, right? And this means we can keep going as these first guys get served, right? Persons, okay, right? Well, I don't know, maybe they're dogs or I don't know, whatever. But they get served, so we move this pointer again, and this we can fill out. So basic idea is this, we can fill out this, so we can remove this part here, and we say here, this last guy, right? Is here, right? And again, we are fine as long as there's some space, right? So it's otherwise it's very effective. It's very effective. Fixed size queue, right? And of course, if we want to make a bigger queue, of course, we could also expand the memory for a little bit. But again, at some point, right, we can keep reusing the existing. So we just need these two references, and as long as they don't overlap, right? So hopefully you get this idea. I can show you, if you want to play around with this. I think I had in the materials, this is data structures, yeah, stack and queue. I think I had some visualizations for this, I hope. If I did. Yeah, stack queue visualization. Look at this here, right? This here. This is exactly what I was talking about. You can check it here, right? And queue, right? This means add, push, right? Let's keep going, right? Let's do quicker. Let's make it quicker. It's going to be exactly this, right? I'm just putting some random numbers. Right? So you see, of course, this is exactly what's going to happen. We're going to finish in a moment. Right? So if I dequeue, if this guy is going to get served, I said dequeue. You see? Done. So these are the 2 pointers. Head is 1, right? The queue, head is 2, right? Tail is 11. So I'll add some few more people. It's exactly what's going to happen. Right? And now tail is 0. Right, head is 2, right? So this is the last guy should be, this means the 0 means next guy should go here, right? 5, I'll do 77, right? And Q goes here, means next guy goes 2. So if I do, 4, and Q actually doesn't let me do it actually. It should actually, technically, right? There should be one place here, right? Okay, I'll do the Q 1. Can I do now? Yeah, now, so I guess there's one, it leaves. Technically, this visualization doesn't let you do the last one, but there's space for the last one as well, actually, right? Only then would you be completely full, right? And then you couldn't add any more, right? So this is maybe a little too strict, in my opinion, but technically there should be no reason why not to. You can add one more person here, right? One more item, right? So I'll leave it for you to see how you can do it yourself. Not too hard, right? You just modify this, right? Maybe look at it next time, but what are we going to do next time as well? We're going to look at searching, sorting, so which we already know, because this book covers things we already covered before, and again, so we'll be able to look at some more visualizations of these structures. Okay, so any questions on stack and queue? How you could make it yourself, if you want, but use vector, yeah, or the queue already built in, it's built in already. All right, so thank you. Have a good weekend.